So here we're going to take a look at partition coefficients and their notation. Earlier in some videos, we've written partition coefficients like this. The distribution coefficient for some element I. So I is some element or compound. It could be an oxide or something else. So an element or a compound that interests us. And then it is being partitioned between some phase alpha and another phase beta. And this is defined as the concentration of I in alpha divided by the concentration of I in beta. And if a mineral is involved, then the mineral is almost always in the numerator. But for our purposes here, for the notation, it really doesn't matter. If you look at older literature published in the 1970s or 80s or before, you will sometimes see this written as KD. Now this goes along with a collection of other Ks. We have K sub EQ, where we have a formal equilibrium constant. We've talked about that in other videos, and then KSP for solubility product, which we've also talked about in other videos. Then there's K sub W for the dissociation of water, or Ka, the dissociation of acids. We haven't discussed that. Let's say you have an acid like HCl. Well, it can dissociate into hydrogen ion plus chlorine ions. And how strongly does that dissociation take place? Well, you could express it as a Ka, where you'd look at the concentrations of the products over the reactants. So just products over reactants, that's not really our concern here. But the value of this kind of value for Ka is you can compare the Ka for, let's say, sulfuric acid or nitric acid or silicic acid and compare it to HCl. And it's a way of weighting how strongly these things will dissociate, how strong they would act as acids. So these things have various uses. Now the Kd is a similar kind of thing, although it's a little bit more abbreviated. The reason probably that we've let go of Kd, although I've not looked at the history of this, is because they're not really specifically associated with an equilibrium or a reaction. And so instead of using the K sub D, there might be an equilibrium that's controlling these concentrations, but since that equilibrium is not specifically expressed and we don't know all the phases and components that are participating in this kind of distribution coefficient, then instead of using the K sub D, I think the idea is that this is a little bit misleading, so instead we use D sub I. So just to say that anywhere we use K, there's usually some kind of equilibrium or an equation that we can write, kind of like we did down here. So HCl is dissociated into hydrogen plus chlorine. Here we're just looking at the ratio of concentrations. There will always be a hidden equilibrium of some kind that's controlling those distribution of the element between phases alpha and beta. But if it's not being specified within the calculation of this kind of coefficient, then we disregard the use of K and we just use the abbreviation D.